Hello there. I want to today look at exercise 5F. Now, exercise 5F is where we do something we did in exercise 5E.2, but using a different method. Now, if you might recall in exercise 5E.2 that we tended to get equations, for instance, like this: 2x cubed minus x plus 1 equals 0, and they give us three roots, p, q, and r, and they say to us, now find the equation with roots p minus 2, q minus 2, and you get this this link between the original roots and the new roots. And we, to be honest, with quadratics this is quite easy what we did at exercise 5E.2, but with cubics and certainly quartics it gets horrendous. So there's an alternative method, and so I want to show you this, and we call these transformations. And essentially we say that well, the root, if you like, a value of x that goes into this that will work. We want this to work with p minus 2 instead. So I'm going to say x is equal to the p minus 2. And if that's true, and then what you get effectively, you're able to move this over here, and you get, if you like, p is equal to x plus 2. Notice the sign changes, obviously. And the whole point about this, I suppose, is that we know that when you put p into this, it's a root. That means the equation effectively works. So I can substitute now this into this equation. Rather than it being x, I'm going to put x plus 2 into my equation. And as I say, the whole tenet of this is that a root will go into this, giving you the answer 0. So I've now written p, my root, as x plus 2, and it will still equal 0. So I know therefore that 2 lots of x plus 2 cubed minus, so notice the x has been replaced with an x plus 2, and the x is replaced with a x plus 2 as well, plus 1 equals 0. Now this is a relatively quick method. Notice how at the moment it's just an algebra thing, so I've got to multiply this out. That's the hardest thing, I suppose. You know, there's a variety of ways to do it. You could use the binomial theorem, or you could over here just write x plus 2 squared equals, well, obviously x squared plus 4x plus 4. And if I cube it, this is why I think it might be better using the binomial theorem perhaps, but there's no problem with doing this. It's obviously what we just got times by x plus 2 again. So I've just got to times this by x plus 2, and I think I'll get x cubed plus, well, x plus 2 times, well, x squared times that gives me 2x squared. 4x times x gives me 4x squared plus 8x, and then 4x and 8. As I say, I think binomial theorems definitely, if I was doing this myself, I'd probably do that. But one way or the other, get that multiplied out, multiply those out, and that's what I've got there. So probably that's the hardest thing to do on this. So up here I'm going to write, it's 2 lots of that. Don't forget it's a minus x and a minus 2 if I get rid of that bracket, and a plus 1, and all that equals 0. So what do I get if I multiply that out? Therefore my equation becomes 2x cubed plus 12x squared plus 24x. Don't forget then I have to take away an x, that's plus 23x, plus 16 minus 2 is a plus 14, plus 1 is 15. That is the equation I wanted. That was, I think, quite simple. So that's the answer. 12x squared. Oh, that's don't know why that's come out as a p. That should have been an x. That looks right to me. Now, just to give you some kind of context of what this means, I've drawn the first graph into my calculator. This is the graph of. I'm just going to show it here. It kind of does this. This is the first graph. This is y equals. It doesn't quite touch that according to my calculator. It might be very close actually. y equals 2x cubed minus x plus 1. And what I wanted, well, it had roots. Now, admittedly, I think one of them, that's the p. The q and the r, it seems, are both complex. They are complex roots because it doesn't actually come down and touch it again, but they're associated with that. But notice what we wanted then was to find the cubic equation with roots p minus 2. So basically, whatever this was, say this was minus 1, I don't know what it is actually, but it looks around minus 1-ish. But I want then to make it 2 less than that, so I want to make it over here. So if I just change the colour of my pen, I want to make it here, which is p minus 2. And of course my q and r are complex roots, but they are also going to get smaller. So this is what it says my new picture is. And I'm just doing it here. I've done it quite badly, but the idea is they are the same curve. This should have been exactly the same as this, but this is my curve now. Y equals, and I've typed this in, y equals 2x cubed plus 12x squared plus 23x plus 15. You can see, yeah, it probably does cross at 15. You know, and I'm saying to you, whatever that was there, this is now 2 less than that. That's what we're doing. We're finding this new equation, this new, in this case, cubic equation, which kind of matches it, but is in each case 2 to the left. So let's see if we can do a few more using this transformations method. So we've got a quadratic this time. The quadratics are nice, I'll be honest. It says this is my quadratic with roots alpha and beta, and I want a new quadratic with roots alpha squared and beta squared. And they're always going to be the same or very similar. There's a link between them. So I'm going to start off a bit like last time. I'm going to say alpha equals x equals alpha squared, sorry. Now, and then I want to rearrange it because I know alpha will go in. By the way, I could have used beta, but you always use alpha. And so I'm going to rearrange this. I reckon alpha is the square root of x. And alpha will go into this and give me 0, so therefore, what will it do? Well, I'll just substitute that root x in. Root x goes into there. I will have, well, it says x squared. Now, I'm going to get root x squared plus 2x, it says, but I'm going to substitute that root x in instead. 2 root x plus 3 equals 0. Now, of course, we can play around with this. So what do I get? If I square root, then square it, I get x. Disappears. Then it's plus 2 root x plus 3 equals 0. And I'm trying to get a quadratic. And I suppose at the moment, I want a quadratic, but it clearly isn't a quadratic. So I've got to do something to make it a quadratic. And the technique is to get the square rooty thing onto the other side. So I'm going to write x plus 3 equals minus 2 root x. And then what I do is I square both sides. So x plus 3 all squared on this side, and it's going to be minus 2 root x squared on this side. And if I do the left hand side, I'll get x squared plus 6x plus 9. And if I do the right hand side, well, minus times a minus is a plus, so the fact it was minus didn't actually matter. I think it's 4, and root x times root x is x. Move those over there. X squared plus 2x plus 9 is equal to 0. So that's what I reckon. You know, it's very similar to what I started with. We've just added 6 almost. It's gone from 3 to 9. But that's what I think the answer is. Now I've got actually a method here somewhere. Let's see if it's the same. Interestingly, I used a different letter, but that you can use whatever letter you like. So to get used to that, you might see examples where, well, particularly if you look at mark schemes and stuff, U is quite a common letter to use. But more recently, I've seen them using X a lot more. Notice they both say equals 0. It's any old quadratic, so both are right. Here's another one then. So we've got 7x squared. It's quadratic again. I do like quadratic. They're relatively straightforward. So I've got this. So again, you'll notice it's p squared q squared from p and q. So I'm going to start off by saying x has to be p squared. Therefore, p equals root x again. So it's the same technique really, isn't it? And we can substitute this into here. So I get 7 lots of root x squared minus 2 root x plus 5 equals 0. And do you remember what I did last time? I moved this onto the other side. So, well, before I do that, I'll just tidy it up, I suppose. It's 7x minus 2 root x plus 5 equals 0. Because the square root squared disappears, the problem. And then I'll move it over. 7x plus the 5 equals 2 root x. So the negative is there, so it's now a positive. But as I said, it doesn't really matter. It becomes positive when I square it. Now, square both sides. Well, I reckon I'll get 49x squared plus 35 doubled 70x plus 25. And I reckon that will be equal to 4x on this side. And move those over. 49x squared plus 66x plus 25 equals 0. So it's much bigger numbers than last time. That's what's the answer. This is exactly right. Okay, so you're getting perhaps the idea of how to do these. We've got loads of different types though, unfortunately. So here, I'll just carry on with this. So you start off on this one. We want to make it 1 over alpha. So I'll write x equals 1 over alpha. And therefore alpha equals 1 over x. I sub those in. So rather than x squared, I write 1 over x squared. Plus 2 lots of 1 over x plus 3 equals 0. So obviously this is 1 over x squared plus 2 over x plus 3 equals 0. And the trick here is to times everything by x squared. And you just notice if you do that, it just simplifies into a nice quadratic. And that's what we want, of course. We want a quadratic. So x squared times that by 1. If I do this, I get 2x. And this, I get 3x squared. Notice where the powers are is all the other way around. So my final answer, I reckon, is 3x squared plus 2x plus 1 equals 0. It's relatively quick and easy to do. So, and that's in use, but it's just the same answer. Now, sometimes the questions are what I would describe as a direct substitution, where they actually explicitly give you this substitution to use. Now, here it says use this transformation to get the simplest cubic equation for u. So I suppose I've got to keep u in my answer. And so we are literally going to substitute this in. They've done this substitution bit for us already. So rather than x cubed, I'm just going to write u over 3 cubed. So it's slightly different from what we've seen before, because it tells me the substitution. Doesn't talk about roots, does it? It just says, here's the substitution to use. Okay, therefore I'll do it. 8u over 3. And it does say I want the equation to be in u, so I don't want to get it in x. Okay, let's multiply that out. U cubed over 27 plus 2u squared over 9, nearly made a bad mistake, plus 8u over 3 minus 4. And I think what I want to do is times everything by the 27. And if I do that, I will get, I think u cubed, 2/9, I reckon 6u squared, 8 over 3 times 2, I reckon plus 72u minus 108 equals 0. So let's see, and that's right. Now it does actually say write down the roots of your cubic equation in terms of alpha, beta and gamma. And of course we had this here, but the actual u, if you like, you can move that over, and therefore u would equal the 3x. And for that reason, notice I've put at the bottom my roots would become 3 alpha, 3 beta and 3 gamma. It's the other way round to what we've seen before. So we'll have another look at this one. I don't think I'm going to get time to do this one, actually, just looking at this. But you'll notice again it says x equals root u. So what I'm going to do is I'm just going to substitute that in, root u cubed. That will cause us a few problems. 2 lots of root u squared plus 8 root u minus 4 equals 0. And of course I've got to convert that into a cubic. At the moment it's not a cubic equation. So we're not going to finish this now. We'll do that in a lesson. We've got, that's that one I think. And then we're ready to do exercise 5F. So I'll do a couple of examples. I'll finish that one and do a couple more examples in class. And then hopefully you'll be able to do exercise 5F. Thanks guys.